So this matrix A, we want to decompose into LU form, LU decomposition, or LU factorization, same thing. The idea is we want to rewrite matrix A as some matrix L that's purely lower triangular, and some matrix U that's purely upper triangular multiplied. So L being purely lower triangular means we can have stuff in the lower triangle below the main diagonal. We might or might not, but the important thing is everything above the main diagonal must be 0. And then you could have anything on or below the main diagonal. You don't have to have non-zero numbers down here though. For instance, a matrix consisting of all zeros technically consists as lower triangular because everything above the main diagonal is 0. Likewise, an upper triangular matrix just means anything that's below the main diagonal is all zeros. And then anything on the main diagonal or above, no restrictions. Those could be anything, possibly including 0. But the idea is we want to take the original matrix A and split it up to factor it into a purely lower triangular matrix times a purely upper triangular matrix. And how do we do that? What would be a good way to get one or the other of these matrices from the original matrix A? Is there any way we could turn this matrix into purely lower triangular form or purely upper triangular form?
I believe we can. Would we just have to use like elementary row operations and try to get into that form?
Yeah, exactly. We already have seen the idea of using row operations to cancel out stuff under the pivots, for instance, and that will turn it out into upper triangular form. So we can start by doing that. The idea is for LU decomposition, or at least one way to do it, is to use row operations to eliminate everything under the pivots. So use row operations one at a time to turn A into upper triangular form. And then we can use the row operations we did to build an L matrix also, a lower triangular matrix. So let's try this one step at a time. If we start with the idea of finding the pivot in the first row, the first non-zero number we encounter is 1. So we're going to call 1 the pivot of the first row. And we want to use that to eliminate everything else in the same column. So what operations will accomplish that? What multiple of the first row can we add to the second row to cancel out the 6?
We can subtract 6 times. Well, we can add -6 times the first row.
Yeah, that should work. -6 times the first row added to the second row should cancel out that 6. So let's see what that becomes. First row, we're not changing. Second row, 6 minus 6, 6 minus 24, -3 plus 18. And then third row, we're not changing it. And then what's another operation we can do here? What operation could we do to turn to use that pivot to get rid of the 5 here?
First row times -5.
Yeah.
If we add -5 times the first row to the third row, 1 times -5 would cancel out the 5 here. So let's see what that turns into. And if you're in a hurry, these could be combined into one step. Like we could just say, we're adding a multiple of row 1 to row 2, and in the same step, also adding a multiple of row 1 to row 3. I find it kind of useful to write out each step individually so we can look at what's going on in between, but you could do both of those in one step without having to write out the in-between one. But I'm just writing out all the steps just to be sure about it. So in this step, we're not changing the first row or the second row, but we're modifying the third row by adding -5 times the first row. So 5 plus -5 times 1, 1 plus negative 5 times 4, that's 1 minus 20, so negative 19. And 1 plus 15 would be 16. So that matrix is now, or at least this pivot is now alone in its column. So we're good with this column. This column is pretty much done. What is our next pivot? If we start in the first row, the first non-zero number we encounter is a 1. What about in the next row?
Would that be the negative 18?
Yeah, the negative 18. Because we're going across, first non-zero number we encounter is this negative 18. And so we want to use that negative 18 to eliminate, if we were going all the way to reduced row echelon form, we'd want to eliminate everything above and below. But in this case, we don't need to go all the way to reduced row echelon form. We just need to go to upper triangular form. We just need to eliminate everything under the pivot. So now we just want to make some operation to the third row that will cancel out that negative 19 there. So what operation using this negative 18 would cancel out the negative 19? If we want to have the negative 19 that's already there plus something times negative 18 equaling 0, what multiplier will make those cancel out? Yeah, 19 over 18. You can always turn any number into any other number by multiplying by the number you want over the number you don't want, because that'll cancel out the 18 and introduce a 19. Also, we're going to need a negative here as well, because that way these negatives cancel out. We get positive 19, which will cancel out the negative 19. And of course, we want to do this to the entire row. So we're going to add negative 19/18 times the second row to the third row to get our new third row. And let's see what that becomes. So first row, we don't need to change any further. Second row, we can keep as is. Third row, we've got 0 plus negative 19/18 of 0 is still 0. That's one of the nice things about using a row that already has the 0 established from previous steps. This 0 isn't going to change the 0 we've already got. Then negative 18 times negative 19/18 is positive 19, which cancels out the negative 19. And lastly, 16, I probably want to write this one down, 16 plus negative 19/18 times 15. And some of this reduces because 15 and 18 are both multiples of 3, for instance. So we can write that as 5 over 6. So we'll want to write the 16 in terms of sixths also. 16 is what, 96 sixths? Plus negative 19 times 5 would be 95 sixths. Oh, so we just get 1/6. So we've now gotten rid of everything under the pivots. This is now in upper triangular form. Everything below the main diagonal is all zeros. And we don't really care what's above the main diagonal other than keeping track of it. So this matrix we're going to call matrix U. Any questions on that so far? Now to figure out matrix L, the lower triangular matrix that can be multiplied by U to find A, there's many ways of doing this, but one of them that this textbook really focuses on is taking a look at the exact operations you did to build matrix U in the first place and undoing those. Algebraically, we can write this as, we started with matrix A, and we applied some transformation to it. Specifically, we applied the transformation add negative 6 times row 1 to row 2. So let's call that transformation this step we're going to call, let's say, E1. E1 in the sense that it was the first elementary transform we did to this matrix. And the important thing about these elementary transforms, these elementary row operations, is that each one of them can be written as left multiplying by a certain matrix. So we can turn matrix A into this matrix by left multiplying by a certain transformation matrix. And what would that matrix be? What matrix would have the effect of adding -6 times row 1 to row 2? What would that look like? It might be helpful to look at this in terms of what's not changing. In this first step, what is not changing about matrix A?
Rows 1 and 2.
Yeah.
I mean 1 and 3.
Well, we are changing row 2, but we're not changing
I mean row and 3.
Right. Rows 1 and 3 stay exactly the same. And what's a matrix that doesn't change what you multiply it by?
An identity matrix.
Right. So if we don't want to change the first and third rows, we can take just the first and third rows of the identity matrix. The idea is if you multiply just the first row times each column, let me actually write this out. If you were to multiply this out, you'd be multiplying 1 times 1 plus nothing plus nothing. 1 times 4 plus nothing plus nothing. 1 times -3 plus nothing plus nothing. So this 1 is getting multiplied by the entire first row, and then we're not adding anything from the second and third rows. So 1, 0, 0 means take the first row exactly as is and add nothing from the second row, nothing from the third row. In other words, don't change the first row. Likewise, this third row, 0, 0, 1, nothing plus 1 times 5. Nothing plus 1 times 1. Nothing plus 1 times 1. This 1 is getting multiplied by the entire third row. So this is just saying, take no information from the first row, no information from the second row, and 1 times the third row exactly as is. In other words, don't change the third row. But we are changing the second row. How would you write out add -6 times row 1 to the second row as is? In terms of, sorry, go ahead.
Oh, yeah. I was going to say -610.
Yeah, exactly. Because if you were to multiply that out, this -6 would be multiplied by something from row 1. So we get -6 times something from row 1 plus something from row 2 exactly as it is, plus nothing from row 3. This row could be thought of as instructions or a recipe for building the new second row. Specifically taking -6 times the entire first row, adding it to the second row exactly as it is, and then no information from the third row. So this is E1. This is the elementary transform matrix that has the effect of adding -6 times row 1 to row 2. Any questions on that so far? So that's E1. And notice that this is in the lower triangular category because it has nothing above the main diagonal. So this elementary transform matrix, because we're using a higher row to influence a lower row, is guaranteed to be lower triangular. That's really useful because we can use that as a step in building the lower triangular matrix L. But of course, that wasn't the only row operation we did. After we did this, so this matrix is E1 times A. We then did another operation. We took E1 times A, the result of the first operation, and then applied another operation, which we could call E2, the second transformation we did. And again, that transformation, that elementary operation can be written as left multiplication by another matrix. And how would you write out matrix E2 here if all it does is -5 times row 1 added to row 3? That's going to look exactly like the identity matrix, except for what change?
In the last row, the first number, which is 0, would be -5 instead.
Yeah. This -5, and then the rest of the identity matrix as is. negative 5, 0, 1 means take negative 5 times the first row, add that to the third row, and then take no information from the second row. That's your instructions for building the new third row. Then everything else, we can just keep the rows of the identity matrix. In fact, every elementary transform matrix should look like the identity matrix with one small change made to it. In particular, that one small change is just that operation. We can build this matrix alternatively by taking the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1 and making this change to it. Adding negative 5 times the first row, negative 5, 0, 0, to the third row to build the new third row. So this is another way to build the elementary transform matrix. Take the identity matrix, apply whatever transformation you're talking about to the identity matrix itself, and that is the elementary transform matrix we're talking about. Any questions on that so far? And then E3, because what we now have, this matrix is E2, E1A. That is, we started with matrix A, we applied transformation 1 to it, and then we took the result and applied transformation 2. Now we're going to need to make one more transformation, which we're going to call E3. And we can do that the same way. We start with the idea of the identity matrix. We make this one small change to it. Specifically, we're going to have a negative 19/18 in the second spot of the third row, because we're modifying row 3 by adding a multiple of row 2 to it. So negative 19/18, and then identity matrix everywhere else. So this would be matrix E3, the third transformation we did. Any questions on that so far? So we applied those 3 transformations to matrix A, and the end result is this matrix U. But we don't want something times A equals U. We want to write this as A equals something times U. So how could we get rid of these 3 transformation matrices? What's the opposite of multiplying by a matrix?
Dividing by a matrix.
If it were just a scalar, yes, but you can't really divide by a matrix, but you could multiply by what? What can you multiply by that will cancel out a matrix? Or let's look at this in terms of numbers. If you just had like, let's say you have like 5 times x equals 20. And of course, pragmatically, you just divide both sides by 5 and get x equals 4. Can you do that without division, though? Can you describe a way to solve this equation without saying anything about division? Is there anything you could multiply by that would cancel out the 5?
You can do 20 over 5, right?
Well, that wouldn't cancel out the 5, though. If ultimately we just want x equals something, what could you multiply both sides by that would cancel out the 5? What could you multiply by 5 by? Yeah, multiply by 1/5. If you multiply both sides of this equation by 1/5, or if you don't want to write it as a fraction because fractions are technically just a shorthand for division, you could write it as 0.2. So if we just multiply both sides by 0.2, what's 0.2 times 5? Yeah, that's just going to be 1 times x, and then 0.2 times 20 is going to be 4. And 1 times x is just x. So this solves the equation without technically using any division. All we're doing is multiplying both sides by a number that is the multiplicative inverse of 5. And we can do the same thing with matrices. We can say we can't divide by a matrix, but you can multiply by the inverse of a matrix if that matrix is invertible. And ultimately, the only reason why we say you can't divide by a matrix is because not every matrix has an inverse. When we say divide by 5, that's essentially the same thing as saying multiply by the inverse of 5. And you can do that because 5 has an inverse. Every number has an inverse except 0, of course, but that's just the one exception. But for matrices, you wouldn't really want to say divide both sides by the matrix because not every matrix has an inverse. Many matrices do not have inverses. So we don't really want to try defining a division operation on matrices because inverses are not universally defined for matrices. However, we can multiply by the inverse if there is an inverse. And it turns out these elementary transform matrices, because they just represent one simple operation, that operation can be reversed. For instance, what's the opposite of adding -6 times row 1 to row 2? How would you undo that? Like if we just added -6 times row 1 to row 2 and got this, but then we decided that was a mistake and we wanted to backtrack, how would you modify this matrix to get back to the original?
Would you just do -1/6 times row 1?
That wouldn't change back to the original though, because if you add 1/6 of row 1 to row 2, you're going to be adding like 1/6. You get 0 plus -1/6, -18 plus -4/6. That doesn't get back to the originals. But what would you add to get back to truly the original values here? Think of it additively, not multiplicatively.
Oh, okay. So if you add like a -6, would you subtract a -6 instead?
Yeah, you could just subtract -6 or add +6 times row 1. So the opposite of adding -6 row 1 to row 2 is adding +6 row 1 to row 2, which means if we wanted to write out the inverse of E1 inverse, that's exactly the same except make this -6 +6 instead. So if you take this matrix and left multiply by this elementary transform, you'll get back to the original because you'll be canceling out the effects of operation number 1. Same thing here. Our next step was add -5 times row 1 to row 3 to get to the next step. To undo that, we could just add +5 times row 1 to row 3. So E2 inverse is going to be exactly the same, but with a +5 in the lower left instead of a -5. Likewise, the third operation was add -19/18 times row 2 to row 3. To invert that, we'll just be adding +19/18 times row 2 to row 3. So inverting an elementary transform matrix is remarkably straightforward. All you have to do is take whatever that one change is and reverse it. So if it was a negative, make it positive. If it was positive, make it negative, and keep everything else the same. So, and that's ultimately just because each one of those elementary transform matrices represents one single step. And that one step is completely reversible. So each one of these matrices can be inverted. If we wanted to cancel these out, which one should we cancel out first?
E3?
Yeah, E3 was the last one we did, so it's the first one we have to undo. And this is very much like the order of operations thing where in an equation you're solving for a variable, typically the last thing that was done to the variable is the first thing you want to undo. Let me write this a little more tidy. We have A left multiplied by E1 first, then E2, then E3, and that equals matrix U. The first thing we want to get rid of is this E3, and we can do that by left multiplying both sides by E3 inverse. That way, since E3 inverse and E3 are adjacent to each other, we can cancel those out. Formally, we'd say E3 inverse times E3 is the identity matrix, but the identity matrix times anything is just itself. So E3 inverse times E3 we can now ignore. We can say those cancel out to the identity matrix, and that no longer influences the result. And then we now just have E2 times E1 times A equals E3 inverse U. How do we get rid of this E2 next? We can just multiply both sides by what?
E2 inverse.
Yeah, if we left multiply both sides by E2 inverse, and I'm saying left multiply because order matters here. We've got to keep track of which side we're multiplying on. So we're left multiplying the left side of the equation by E2 inverse, and we're left multiplying the right side of the equation by E2 inverse. Same operation to both sides. But E2 inverse times E2 is also the identity matrix. Those effectively cancel out. Formally, we would say these multiply to the identity matrix, but I times E1 times A is just E1 times A. So we can pragmatically just say these cancel out. And we're left with E1 times A. And then what's the last step we need to do to isolate matrix A?
Times by E1 inverse.
Yeah, left multiply both sides by E1 inverse. And again, E1 inverse times E1 is the identity matrix. So in a very practical sense, we can say those cancel out. Meaning we're left with a formula for matrix A. We can say matrix A can be written as E1 inverse, E2 inverse, E3 inverse times U. And since each one of those elementary transform matrices was lower triangular, their product is also going to be lower triangular. We can combine those all together, and we have values for those. We now have written out E1 inverse, E2 inverse, E3 inverse. If we multiply them together in that order, we get a purely lower triangular matrix that we're going to call matrix L. So multiply this matrix times this matrix times this matrix, and that'll be the L matrix. Meanwhile, the U matrix is just what we got from row reduction in the first place. So your final answer here would be to write out matrix A equals L, whatever you get from multiplying these together, times matrix U. You should get a purely lower triangular matrix and a purely upper triangular matrix. And of course, you can always check your answer by multiplying those out and make sure they get back to the original matrix. Any other questions on that? So that's the basic idea of LU decomposition. And this is just one example of a factorization of a matrix. There are many ways to factor a matrix. In other words, to split it up into two or more other matrices multiplied together. We're going to look into, I think, 2 or possibly 3 other ways of factoring matrices later on in the quarter, which have other uses as well. But this one, LU decomposition, I don't really know of much actual practical use for it, other than one way to use it is you can use it to sort of justify the idea of row reduction as a way of solving a system of equations. The LU decomposition is sort of the background theory of why row reduction to solve a system of equations works in the first place. But the other factorization methods are much more applicable in certain other branches of mathematics as well. One of the big ones we're going to see is diagonalization, which is a way to rewrite a matrix as a purely diagonal matrix with some modifications to it. And one of the big advantages of that is that it makes it much easier to raise a matrix to a power. Like if you wanted to raise matrix A to the 5th power, multiplying A times A times A times A times A would be really tedious. But diagonalization provides a much faster way of raising A to a large power. The process of diagonalizing it in the first place, the process of factoring it, can be pretty tedious. But once you've factored it, raising A to a large power becomes very easy to do. So a lot of the factorization methods are stuff like that, where the process of factorization is tedious, but once you've done it, then there are a whole bunch of operations you can do to the matrix that are much easier because it has been factored. Any other questions on this factorization stuff so far?
None from me, thanks.
All right, let's take a look at the null space then. And we're going to often, the null space is specifically a collection of vectors. A space just means a set of vectors that follow certain rules. And the null space of a matrix in particular is a space, a set of vectors that have a certain property. The null space of a matrix, now let me put in the dimensions here. Let's say this matrix is M by N. So M is the height, and N is the width. The null space of a matrix is the set of all vectors, let's say all vectors X, such that what property does a vector have to have in order to count as being part of the null space?
Part of the 0?
Yeah, specifically if you multiply matrix A times that vector, the result is 0. And I usually think of this in terms of treating A as an operation. If you take matrix A and multiply by some vector, the result is going to be some other vector. Let's call that vector Y. And you could think of this as, if you think of A as an operation, a function, a transformation, whatever you want to call it, that takes vector X as an input and gives you some other vector Y as an output. So you can think of A as an operation that turns some vector into some other vector. And in particular, if A is M by N, what dimensions does X have to be in order for these to be even possible to multiply?
N by M?
Yeah, X has to be, well, N by something, because the inner dimensions have to match up. And if we're treating X as a vector, presumably it's just a single column. So let's say N by 1. So if A is M by N, then X has to be N by 1, because the inner dimensions have to match up. That is, the width of the matrix has to equal the height of that vector. And presumably the width of the vector is 1 because it's just a single column. In that case, what would the dimensions of vector Y be? What would be the dimensions of that output?
M by 1?
Yeah, M by 1. The inner dimensions matching tell you this can be done. The outer dimensions tell you the dimensions of the result. So you can think of matrix A as an operation function that takes an N by 1 vector as input and turns it into a different M by 1 vector as output. And of course, if this is a square matrix, if the dimensions are the same, like 5 by 5, then it'll take a 5 by 1 vector and give you a 5 by 1 vector as output. A different 5 by 1 vector, presumably. So a square matrix has inputs and outputs that are the same type of vector, the same universe of vectors. But the matrix in general can be thought of as a transformation that turns an input vector into an output vector. And that input has to be N by 1. So I'm going to say X, which is a member of R to the N. So we're looking for vectors that are members of R to the N. So N by 1 real numbered vectors that have this property that when you multiply A times this input, the output is 0. Because in general, if you just multiply matrix A times some vector, you could get any vector as output. But we're specifically looking for only the inputs that cause the output to be 0. So in a way, this is very much like finding the roots or zeros or intercepts or whatever you want to call them of a function. We're looking for all the inputs that cause the output to be 0. And we call the collection of all the inputs for which the output is 0 the null space, the set of all vectors that turn into 0 when multiplied by A. This is sometimes referred to as all vectors that are mapped to 0. We sometimes refer to a function as a mapping. Like we would say, this operation maps X to Y. It maps the input to the output. So we're looking for all of the inputs that are mapped to 0 as the output. Any questions on that so far? Just the definition and the terminology.
Nope, that makes sense.
All right. And if you have the collection of all the vectors that get mapped to 0, get turned into 0 by multiplication by the matrix, then they have some very important properties. One of them is if you add two of them together. Like let's say we know that A times x1 is 0, and also A times x2 is 0. In other words, we're saying x1 is a member of the null space and x2 is also a member of the null space. If you add them together though, and multiply by matrix A, what's going to happen?
It will no longer be a member, or
Well, let's check. If you're multiplying A times a summation, what can you do with this A times? What
split
can-
it up and
Yeah, this can be split up, right? The distributive property still works for matrices and vectors. A matrix times something plus something can be split up into matrix times the first thing plus the matrix times the second thing. And what were we assuming about A times x1 and also about A times x2?
that they're both 0 and
Right.
that they're both in the null space.
Exactly. Since x1 was a member of the null space, that means A times x1 is 0 by definition. We were assuming x2 is a member of the null space, so A times x2 is 0 by definition. And 0 vector plus 0 vector is still the 0 vector. So it looks like A times the summation is also 0. In other words, if x1 is a member of the null space, that is, it gets turned into 0 by multiplication by A, and if x2 is also a member of the null space, then their summation, x1 plus x2, is also in the null space. It also turns into 0 when multiplied by A. So this is one of the very important properties of the null space. We say it is closed under addition. Null space of a matrix is closed under addition. And when we say a set of things is closed under addition, we just mean you cannot leave that set by just adding things together. If you take two values that are in that set and add them together, you're not leaving the set. The result of adding them together is still part of this set of things. It still has this property. It's also true that this is closed under scalar multiplication. If you say, let's say R is a real number. If you take real number R times vector x1, which we're assuming is in the null space, and you multiply that by A, any scalar, any real number that's mixed up here, you can rearrange where it is. Matrix multiplication you can't rearrange, but multiplication by a scalar can be rearranged. So this can be rewritten as the scalar times A times x1. And what were we assuming about A times x1 from the start?
That is 0.
Right. So we get that real number times the 0 vector, which is still the 0 vector. So we can also say that the null space is closed under scalar multiplication. If you take a vector that's a member of the null space, that is, it turns into 0 when multiplied by A, and you multiply it by any real number, the result also has the property that it gets turned into 0 by A multiplication. So if any vector is a member of the null space, then any scalar times that vector is still a member of the null space. So we say that the null space is closed under multiplication also. And those two properties, closed under addition and closed under multiplication, are part of the definition of a space. The reason we call this a null space instead of just a null set is that it has these properties. A vector space is a collection of vectors that has those properties. The closure under addition and closure under scalar multiplication. In fact, in a way, I think you could say that the whole idea of a vector space is basically building on the concept of, well, what if we have more collection of vectors that act like this? More collection of vectors that have these properties of closure under addition and closure under scalar multiplication. Any questions on that so far?
No.
One other really useful property of the null space, if you have a vector in the null space, we know that it multiplies to 0 when multiplied by A. But let's take a look at how that multiplication works. Let's say you've got some matrix A, B, C, D, E, F, G, H, I, and you're multiplying it by a vector X, Y, Z. And we want to assume that this equals the 0 vector. But let's take a look at the mechanics of multiplying that out. If you're actually multiplying this matrix times this vector, what values are you combining? Like, how would you multiply this matrix times this vector?
Like doing XYZ times the rows.
Yeah,
Okay.
combining an individual row with X, Y, and Z. So for instance, going along the first row and first column, we'd have AX plus BY plus CZ. And likewise, second row and the only column, DX plus EY plus FZ. And third row, GX plus HY plus IZ. And the important thing is we need each of those to equal 0 in order for XYZ to really count as a member of the null space. But let's take a look at what we just did there. When we were combining, for instance, the row ABC and the column XYZ to get this, what operation was that? What do we call that way of combining these components and these components?
Like matrix multiplication.
Overall, this is matrix multiplication. But if we take a look at just this row and this column, in fact, for the moment, let's write this row as a column, A, B, C. And then we have this other vector, X, Y, Z. Because any row of a matrix, if you tip it up right, it acts like a vector. When we're multiplying A times X plus B times Y plus C times Z, what operation is that?
Dot product.
Exactly. What we just did, the process of matrix multiplication involves taking dot products of individual rows of the first matrix and individual columns of the second matrix. So we just took a dot product and we got 0. What does that tell you? If a dot product is 0, what does that tell you about those two vectors?
I think they're parallel.
Parallel would be if the dot product is very large or if the cross product is 0. But if the dot product is 0, what does that mean?
Perpendicular.
Sorry,
On
what
the
was
degree. Perpendicular.
Yeah, we know these two vectors are perpendicular or orthogonal, whichever term you want to use. So that means that not just this row, but every row, because all of these ended up equaling 0 by definition, every row of the matrix is orthogonal or perpendicular to every vector in the null space. So this is one of the important properties of the null space. Every vector in the null space is by definition perpendicular to every row in the original matrix. And in fact, it's also perpendicular to any linear combinations of rows in the original matrix. Like if you just make some linear combination, like let's say 3 times the first row minus 5 times the second row, and get a new row, that row will also be orthogonal to XYZ or any other vector in the null space. So what we would say there is the null space is orthogonal to the row space being all possible linear combinations of rows. So we'd write that as the null space of the matrix is orthogonal to the row space of the matrix. So null space is all vectors that turn into 0 when multiplied by A. The row space is a collection of all possible linear combinations of rows of the matrix. But since the matrix multiplication process results in row dot column, that means, and of course we're assuming they all equal 0 because it's the null space. That means every row in the row space is orthogonal to every vector in the null space. So because that's true for every possible combination, if you take anything from the row space and anything from the null space, they're guaranteed to have a dot product equal to 0. We would say that the entire null space is orthogonal to the entire row space. This is what it means for two spaces to be orthogonal, that every vector from one of those spaces is orthogonal to every vector in the other space. One geometric example of that would be, let's say you take a look at three-dimensional space. If you have like the XY plane and the Z axis, every vector in the XY plane is perpendicular to every vector on the Z direction. So we'd say that the XY plane and the Z axis are orthogonal subspaces. Any other questions on that?
No, I think that clears it up. Thank you.
All right, sounds good. Feel free to email me if you have any other questions, and we can look into some more examples next time. See you later.